Okay, so your questions. By the way, you can also ask questions about the already handed in homework assignments. So the first assignment is handed in already. So if you have questions, you can also ask them.
On my homework, dq is not always the differential of q, but I didn't get.
You see, what does df mean? Let's assume that f is a function of x. What is df? What's the meaning of it? Or, I mean, in mechanics, we are talking about the position as a function of time. Then we talk about the velocity as dx by dt. What's the meaning of dx?
The change in the curve.
Yeah. For dx is you measure x at a time t, then you let it change for a very small amount of time, and you look at the change in it. So it says that there is already a function of t, or a function, in this case a function of time, and you are looking at how much that function changes. You see, when it comes to dq, there is no function q, so you cannot talk about the change of q. So you cannot define a function q, because we had already seen that if you take two different states, two different macro states of the system, the amount of heat you give to the system depends on how you go from one point to the other point. So if you are trying to define a q for a point in phase space, well, that definition should depend on how you get to that point. But that is not a function of the state only.
It's okay to define differential.
Well, if you would like to do that, you can define q as a function of p, v, t, the macro state, and the path, if you are happy with that definition. But in that case, what does dq mean? Because you see, dq is, if you would like to use this definition, it should mean the change in, if you change your point, how much your function changes. But in this case, well, there is no phase space. I mean, this is not a function of phase space. This is a function of phase space plus all the paths. So you cannot really talk about dq in phase space or in the phase space PV.
Our process, so we can fix the curve in the phase space. We can talk about change in Q.
How do you propose to fix it?
If you give me which process the state system goes over, we can still talk about change in Q.
You see, I can define this function. There's no problem in defining this function, but it will be a function of p, v, t, and the path.
Okay. As long as we can fix the path, we can
but,
still treat it as a function.
Sure. I mean, you see, mathematically speaking, you can talk about this function, and then you can talk about the change in this as you change p, v, t, and the path. It will be a functional of the path. But at the end of the day, what we are interested in is, well, we are trying to describe the state of my system. So that is what our aim is. I want to describe this one. Well, if I want to describe this one, and its current state should be independent of how I get to this final state. That is, the quantities that I am interested in should be independent of how I obtain this one. Then this won't be so useful for me. But mathematically speaking, you're right. I mean, I can always define I can define a function q, but this time it has to be a functional, not an ordinary function. And in that case, I can talk about the very small changes as I change the path, p, v, and t. But it won't be so useful, let's say.
But if we treat q as a variable,
Okay.
So this is something that I'm specifying as a very sort of.
But you see, then you are claiming that let's define my functions, some other function, as a function of Q. Is this what you are saying?
Yeah, that's all.
Okay, what is Q?
The amount of heat that I'm giving.
Given since when?
I have to specify.
Okay, you have to fix the time. Okay, that's not a problem. How do you give this heat? Sure. You see, for example, if you give a given amount of heat to a system at constant volume, all the heat you give will be converted into internal energy. You see, delta U is equal to delta Q minus delta W. If you give this heat Q in a constant volume process, delta W is 0, so delta U is equal to delta Q. If you give it in a process in which the pressure is constant rather than the volume is constant, then delta W will be positive.
Okay, but those details are like system specific, like giving a command to a person. I don't care what does he or she
You see,
spend on.
it's not a system-specific process. It's a system-specific property. It's a process-specific property. And that is kind of the problem. When I'm looking at the system, if I want to describe the system, if I want to study the properties of the system, I don't really care how I obtain it. As I said, you can always come up with an idea like this one, Q as a function of P, V, T, and path, etc. You can always cook up something. But will it be useful for my purposes? Or will it complicate the discussion more than what is actually necessary? And then one of you asked the question, for example, in your reading assignments for this week. Okay, in the sections, it describes the microcanonical ensemble, and then it describes the canonical ensemble, and then it spends a considerable amount of time on discussing why they are equivalent. Why should it do that? Why is it important that those two descriptions are equivalent?
Nature should not like depend on how we describe it. We are describing the same thing.
Are we describing the same thing? Are you convinced that they are equivalent to start with? Okay, there are lots of mathematics going on over there, but did they convince you that those two descriptions are equivalent? And they are equivalent in which sense? For example, in the next step, we will also be discussing the grand canonical ensemble, the third ensemble. And there will also be a discussion on whether the grand canonical ensemble is equivalent to the canonical or the microcanonical ensemble. There we will see that under certain conditions, they are not equivalent to each other. Under certain conditions that are realistically possible, they won't be equivalent. But let's leave that aside for the time being. So are they equivalent? Is it important that they are equivalent?
We weren't trying to just prove that they are equivalent. We noticed that both of the approaches give the same quantities, so we're just trying to see if this is a coincidence or not. So that's the main task. So we did not spend considerable amount of time. Then we spent a little bit extra time to see if this is a coincidence or not. So
Was it a coincidence?
I mean, not so coincidence, but the thermodynamical limit should give the same results.
Are you convinced by your friend's argument?
Even in the thermodynamic limit, the system is completely different. I mean, one is an isolated system, and one is just a closed system. So it seems like they should be different.
But, I mean, do you object to the derivation or the conclusion from that derivation?
No, I don't, but the system is different.
So you're saying that, no, they are not equivalent.
So I would say there is just a coincidence.
It's not. It's the same discussion about coincidence about if we have n particle and n is very high, of the order 10 to the 23rd, then particles being equal on the left and the right of the container, that's not coincidence. That's almost a mathematical certainty. And it's the same situation here. The number of particles is few particles. We're talking about 10 or 1,000 particles. Yeah, I don't think you will find them. You'll find the approaches giving the same results. Here we prove that no, because of the thermodynamical limit, it's not so much coincidence.
How does it prove it that it's not a coincidence?
Limiting case.
Hmm?
Are you asking why the microcanonical ensemble is equal to canonical ensemble under some limiting cases?
Well, you see, the question that was asked, which I think is a good, nice question, is why does the book spend so much time on proving that they are equivalent? Well, I basically have two questions for you. What does the book actually prove to claim that they are equivalent? That is the one thing. And why is it important that they are equivalent? Or under which circumstances they will not be equivalent? But your friend kind of already gave the answer. So what is actually proven in the book?
Does it have to do with how convenient for you to use or to have or not have the Hamiltonian? Because one of them depends on the shape of your Hamiltonian and it goes on.
No, both of them depend on what our Hamiltonian is.
No, the microcanonical depends on your density of states and it goes from there.
Which depends on the Hamiltonian.
Of course it depends, but should I write the Hamiltonian first hand?
Yes, in the microcanonical ensemble Hamiltonian, remember we were calculating the phase space volume. The volume is determined by the Hamiltonian. That is where the Hamiltonian enters into the computation. But your friend, as your friend points out, in the canonical ensemble, the Hamiltonian is explicitly seen. You are integrating or summing over all the states, not just a particular volume, with a suitable weight. But how does the book prove that those two are equivalent? Or what does the book actually prove? You see, if you want to say that two things are equivalent, you first have to define what does it mean to be equivalent. And then you can prove that thing. That is what the book basically does. But what does the book actually prove?
The energy term, entropy term, those are equal, I think. I mean, functions are.
Which functions?
For example, energy.
Okay.
E equals NKT. Something like that. There are several macroscopic properties that are equivalent. That's what I'm trying to say.
You see, in the microcanonical, you see, those equations, although they look the same, they are slightly different. You see, in the microcanonical ensemble, we define the temperature. The temperature is defined through the derivative of the entropy with respect to energy at fixed V and N, from which we could show for the ideal gas that this is equal to Nk over PV. Or whichever way you would like. Oh, no, sorry, not this one, sorry. This is 2/3 Nk over E. This is what we proved in the microcanonical ensemble. Here we have fixed E. In the canonical ensemble, on the other hand, we have the energy is defined as, well, A plus Ts. A is minus kT logarithm of Q, and S is minus the derivative of A with respect to T. This is the average energy. In the canonical ensemble, we have T fixed. and energy can have any value. You see, in the microcanonical ensemble, we have this relation, E is equal to 3 over 2 nkt. For the fixed energy, in the canonical ensemble, we have E, the average of E is equal to 3 over 2 nkt. This is the average. It's not fixed. But this is not enough to show that they are equivalent. The book does one more thing.
He's not.
And the deviation from the average value is proportional to 1 over n. And if n is large, then the E can be considered as fixed.
Yes. First, he showed that, okay, in the canonical ensemble, the energy can take any value. In fact, the state that has the highest probability is the ground state, by the way. But if you calculate the average energy, the energy just does not fluctuate. So then he makes the identification. The E in the microcanonical ensemble should be identified with the average E in the canonical ensemble. Because you see what he does. Let's say in the canonical ensemble, what does it mean? This is in contact with a heat path. That is my canonical ensemble. Its energy, well, I can actually find any value, but the probability of observing the energy of this system at a value that significantly differs from E is 0. So if I pick this up keychain up at a given time and isolate it at that instant, well, its properties do not change, whether I isolate it or not. Of course, with that identification. And I can describe this system, since it doesn't change in time, and the fluctuations from the averages are negligible, I can describe exactly the same thing, either as a system in contact with a heat reservoir, or as a system that is isolated. Of course, the parameters should be related somehow, and the relation is this one. The energy in the microcanonical ensemble should be equated to the average energy in the canonical ensemble. Now, once this proof is done, basically you are free to choose whichever one you like to treat your system. You can either study your system in the microcanonical ensemble or study your system in the canonical ensemble. In the microcanonical ensemble, to treat a system, what we had to do was we had to calculate the volume in the 3n-dimensional space. So we had already done that for the ideal gas. So we had to deal with all these 3n-dimensional solid angles. We had to calculate them. There were all these technical, mathematical mumbo-jumbo that we had to go through. Then we went to the canonical ensemble. You see, the first thing we had, if you have a non-interacting system, if you have the partition function of n particles, if the system is not interacting, it can be written in this form, where Q1 is the partition function of a single particle. In the simple case of non-interacting particles, at least, on one hand, we had to deal with 3n-dimensional volume integrals in the microcanonical ensemble. Now we can just deal with 3-dimensional or 6-dimensional integrals of a single particle. Then, of course, there is a problem of interactions. Okay, in the class, we will be mainly dealing with non-interacting systems, because that is what we can study in a reasonable amount of time during the class. Well, if you want to add the corrections due to the potential, let's forget about quantum mechanical treatment for the time being. Well, in the class, in the microcanonical ensemble, what you had to do is, how does this 6n-dimensional volume change with potential? That won't be a simple problem to solve. But in the case of the canonical ensemble, You see, the potential terms are now in the exponent. If you like, you can just theta expand the exponent, and you can calculate the corrections. So in that case, of course, the partition function will not have such a simple form. There will be interaction, but for example, you can just restrict yourself to two-body potentials. Only two particles are interacting with each other at most. Then you just get a term, add a correction over here, which just requires, Q1 requires 6-dimensional integrals. These two-body interactions would require 12-dimensional integrals. It will definitely be much easier than treating exactly the same problem in the canonical ensemble, microcanonical ensemble, sorry. That is one thing we had gained by this canonical ensemble treatment of thermodynamic systems. There's still the problem of identical particles. You see, here we are still using this n factorial prescription. This n factorial prescription works only if the probability of having more than one particle in the same state, single particle state, is negligible. Otherwise, it will not work. Of course, you can still do a better job than just dividing by n factorial in the canonical ensemble, but it will be much easier to do it in the grand canonical ensemble, which we will study soon. By the way, in your pre-reports, I'm expecting more questions.
There's actually this equation, 357, when he expands e to the power minus beta e.
357.
Yeah.
This one.
Not exactly.
You see, that's one of the problems of using equation numbers.
Yeah, they have different.
Different editions can have different numbers.
But he was expanding. He was expanding e to the power minus beta. So we don't understand the first term. Okay, if we can take the question, I'll just find it.
In the derivation of the density of states, before that, after that.
I'll just find it quickly if somebody would like to ask a different question.
In one of the classes that I was teaching using this method, one day that they had put, there was an ÖSYM exam and they had put a noisy clock. It was quite effective in convincing students to ask questions. In silence you hear tick, tock, tick, tock.
Lastly, I thought I understand, but I didn't understand. About the Lewis theorem in one dimension, or 1D harmonic oscillator.
Okay.
When you equate the units of the axes, P and Q, you don't always have to have a circular shaped path. Say, you were going from 2D to 1D by using a Dirac delta function, but that function included the energy and Q square, P square things.
Okay, so your friends are unaware of what we are talking about now.
You also proposed it at the end of the...
So this is the question. First of all, what does the Liouville theorem tell us? So we started by saying that d rho by dt has to be equal to 0. This is by construction. It's just the number of copies in our ensemble, whether it's any corresponds to equilibrium or not. The number of points doesn't change. It just means this one. Then we said that if the system is in equilibrium, there shouldn't be an explicit dependence. And then we also have, okay, this one also means that d rho by dt plus the Poisson bracket of rho and h. This had to be equal to 0. And then since this is 0, these two just mean that rho h is equal to 0. Okay, one of you were saying that you cannot come up with questions. There is a story of one of my friends who went to MIT for his PhD, and he was complaining that there were no example questions in the book. He was working with a Russian. If you have ever come across with a book written by a Russian, how many of you try to read a book written by some Russian, either in mathematics or physics? There are no examples. Huh? Landau, for example, or even Landau, it has the same problem. There are no examples. And my friend was complaining that, come on, there are no examples here. And his professor was saying, what do you mean there are no examples? You first need to read it. Then close the book and try to follow his reasoning. Can you reproduce it? You will not be able to do that. So read it again. Again, close it. Try it a second time. Again, you will fail. Open it, study it once more. Try it a third time. You might succeed. If you succeed, then ask yourself, how could I modify that example and still solve it? You see, you have at least 3-4 examples now. Okay, so let's come back over here. This was nice because this is actually something I also failed to do when I was studying. We are writing equations. We are writing many equations without really questioning what they mean. Do they make sense? Under which conditions do they make sense? So that is one of the cases that he was, and as far as I can tell, a group of you were puzzled. Okay, so all these equations, they follow nicely, great. What does it mean? So that group tried to come up with rho for simple harmonic oscillator. Now, what are the conditions? Rho h is equal to 0. Well, the easiest solution to this one is that rho should be a function of h. Great. And we can do a microcanonical, canonical, or later on even grand canonical ensemble. Let's stick with the microcanonical ensemble. Now, what does the microcanonical ensemble tell me? Well, the energy is fixed. So in this phase space, rho as a function of P and Q should be 0 if H, P, and Q is not equal to E. And rho is constant otherwise. So basically, the energy constraint gives us a hypersurface in this 6n-dimensional phase space. And rho should be non-zero on that surface and 0 everywhere else.
So
It should be a delta function. So rho P and Q should be equal to rho 0 times Dirac delta E minus 1 over 2 m P squared plus 1 over 2 m omega squared Q squared. So this should be our rho. Then your friend comes out and asks this question. Let's draw this. This is P. This is Q. Well, if you pick any, you have these many copies of the same system at a fixed energy. So they all lie on this ellipse. This is where they should lie. And at any point on this ellipse, Q dot is dH by dP, or P over M, and P dot is equal to dH over minus dH over dQ. This should be equal to minus m omega squared Q. This is also what we used in driving the Liouville theorem. You see, if you remember our derivation, d rho by dt, we just said that this is equal to del rho by del t plus the divergence of, no, sorry, we didn't use this. We first started with this one. No, this is t plus divergence of whatever current we have in phase space. This should be equal to 0. Okay, here we seem to have identified our rho, but what about J? What is J? And in our derivation, if you again remember, we said that J should be equal to rho times V. V is not the speed of my velocity of my particle, but the velocity of these points in phase space. So that gives us del rho by, or this is rho. So V, we said, is P dot Q dot. This is times. This is the V bar vector. So this is where one point where we had a problem, but we just ignored it. D rho by dt plus, well, this divergence is with respect to the coordinates P and Q. So it is a del by del P of rho P dot plus del by del Q rho Q dot. Then we said this should be equal to d rho by dt del rho by del P times P dot plus del rho by del Q times Q dot. These are the three terms which are actually the total derivative of rho with respect to t, plus their additional terms, del P dot by del Q, del P, plus del Q dot by del Q. And this we said is equal to 0 because the system is Hamiltonian. Meaning the system has a Hamiltonian. Since it has a Hamiltonian, it satisfies these Hamilton's equations. And if any system satisfying that equation will have this sum equal to 0. Basically, if you take the derivative of Q dot with respect to Q, that will be the second derivative of the Hamiltonian with respect to Q and P. You can change the order of their differentiations, but then that gives you that this should be 0. Okay, so that was the derivation of Liouville theorem. Then he came and he said, okay, if rho is constant, then he claimed that the speed at this point should be the same as the speed at this point. If there are more fluid coming from one point than the fluid leaving from the other point, then there is an accumulation of points. And you just cannot have, I mean, since we are saying that rho is constant, that cannot be. That was, his idea, his question. Then we said, okay, let's calculate them. You see here, at this point, what is the velocity of this object? Well, let me also write E is equal to P squared over 2m plus 1 over 2m omega squared Q squared. So this point corresponds to P is equal to 0, so that is square root of 2e over m omega squared. And this point is when Q is equal to 0, that is P is square root of 2me. Let's say at this point V is V1, at this point V is V2. And then we said, okay, let me just split this into two. So V1 is P dot Q dot at the point PQ is equal to square root of 2me and Q is 0. So this should be equal to, well, P dot is minus m omega squared Q and Q dot is P over m. Evaluate that the point PQ is square root of 2me 0. And so this is Q is 0, this is 0, and square root of 2e over m. This is V1. What about V2? Yeah, it's the same thing. But evaluate that the point PQ. This time P is equal to 0 and Q is equal to square root of 2e over m omega squared. P is 0, so the second term is 0. The first term is minus square root of, let's say, m omega 2m omega squared e. And definitely, his reasoning was if the density is constant, the inflow should be equal to the outflow. And then he said, but look, the speed of V1 is definitely, which is equal to square root of 2me, which is not equal to square root of 2m e times omega, which is the speed at the point 2. So what's going on?
This is only the speed we need rho times v for j.
Sure.
So rho should be different in those points than the v.
What does it mean? That's the question, basically. Well, let's check your point. Rho dot v at both of those points, are they equal to each other? Magnitude-wise. Well, let's see. Rho times v1, magnitude-wise, and the directions we already know. Well, we said that rho is rho 0, Dirac delta, e minus 1 over 2m p squared plus 1 over 2m omega squared q squared, evaluated at the point PQ is equal to Q is 0, P is square root of 2me, times V1 square root of 2me. So you get square root of 2me rho 0 or Dirac delta 0. That is both expected, but kind of weird. That's not what I would like to have. Let me go through a slightly different route. Let me say that I evaluate this only at q equal to 0. Later on, I will set p equal to square root of 2me. Well, then this becomes rho 0 square root of 2me times Dirac delta E minus p squared over 2m. This is rho times V1 is equal to this one. Of course, in addition to this one, I have to set p goes to square root of 2me. Or let me even, okay, let's give it a try and see if it tells us anything. Well, then we go to, what about rho times V2? This will be rho 0. Again, we have the Dirac delta E minus. Let me just write the Hamiltonian. Well, V2, the speed is 2m e times omega, square root of 2m e times omega. This is V2. And then we are setting q is equal to 0. No, sorry, p is equal to 0. So this will be rho times V2 is equal to rho 0 square root of 2me omega Dirac delta E minus 1 over 2m omega squared q squared. We have this one. As q goes to 0, and we have this one. Well, let's also take this 2m out. Let me leave the p squared alone in both cases. I have rho 0 square root of 2me times 2m times Dirac delta 2me minus p squared. And here we have rho 0 square root of 2me m omega squared e times 2 over m omega squared times Dirac delta 2e over m omega squared minus q squared. So rho V2 is equal to rho 0 square root of 2e over m omega squared times 2 Dirac delta q squared minus 2e over m omega squared. And rho times V1 is just this one. If I didn't do anything, any obvious mistake, rho times V1 is not equal to rho times V2.
These are only the pointers. We need to integrate these to obtain the actual flux.
Well, you see, I don't really need to integrate this to obtain the actual flux. You see, what we know is this one. D rho by dt is 0, but let me write it down, plus the divergence of rho v is equal to 0. So I can just imagine such a surface. Let me not use a S. I can imagine such a surface. I can integrate rho v dp dq over this surface, and this should give me rho v, let me use d omega, over the boundary. You see, boundary has just rho v is a Dirac delta on the boundary, so this will be, let's say, somewhat related to rho v2 minus rho v1.
Can you quickly show rho v1 and rho v2 again? Just 2 lines up.
Now what's going on? What is wrong? Well, if you, okay.
We just calculate E from one of them. If we calculate E from the first one and substitute it into the second one.
Let me just take this, look at this ratio. You see, rho zeros cancel, what I would get, this should be something like omega times Dirac deltas. Right, now 1 over omega.
It's just a clear difference. If we calculate what should E be for the first one and then calculate rho v1 on that point, same thing on the second one, should give same number.
What is your proposal?
So in the first one, I should say that q square minus 2e. Just let's say for this delta function to have a value, q square minus 2e over m omega square should be 0. So I should calculate e, substitute it in the first one, see what rho v in that point. I will do the same procedure on the second line. The number should be the same.
Let's give it a try, but I have serious doubts about that. You see, here we already have a problem, by the way. You see, we have v1 over v2. This is equal to 1 over omega.
Yes, but you already, when you gave that example, when you started to talk about ensemble theory, you said I should expect rho to be different from between these 2 points because one of them is a turning point, so I expect my point to spend more time there. So the other one is faster. I should expect my point to pass quickly through here. I'm not talking about phase space. I'm talking about configuration space. So rho should be different. V should be different, but rho times V shouldn't be different.
Well, you see, let's review that argument in the face of these problems. I mean, okay, we did all the derivations, but somehow in a concrete example, we seem to be struggling. Okay, my argument was this. Is at close to the turning points, so that corresponds to these points, Q is moving slowly. My particle is moving slowly, so it will spend more time at large values of Q, close to the turning points. Okay? But that is a one-dimensional probability. In phase space, things start to get more complicated because there, on one hand, yes, you are right, it spends more time at that value of Q, but you see, look at over here. At that value of Q, it spends a long amount of time, but P is changing fast because its speed is changing fast at that value. So that doesn't necessarily mean that the particle is moving slowly around that arc between the blue lines in phase space. You see, on one hand, we have the probability distribution in position. That probability distribution in position should be peaked close to the turning point. But in this phase space picture, it basically corresponds to, if you just divide the Q into various bins, for that value of Q, the path is quite long. So kind of my argument there was not completely correct.
So if we return to these equations, they calculate E from one of them and E from the other, wouldn't they get the same number?
What do you mean E?
E
Energy.
Yeah.
The energy will be the same.
No, I mean the rho V, rho 1 V, rho V1, rho V2, rho 1 V1. They should give the same number as that case.
Well, let's see. The answer is still, let me find it. You see, V1 and V2, they don't have the same units. Rho has the same unit everywhere. So there is no way rho V1 will be equal to rho times V2. Whatever you do, they will be different because they have different units. So we have to specify what we mean. I mean, if they have, I mean, even the unit changes. Why does the unit change? Well, you see, these two quantities that we use to define V, P dot and Q dot, they have different units. Different components of the velocity have different units. You see, that's not something we are just used to all the time. I mean, when we use the Cartesian, we either use a position space where the units are all meters, or momentum space where the units are kilogram meters per second. Now we are combining the two, defining this abstract phase space, which combines coordinate, well, it depends on how you construct it, but it combines coordinates with different units. So what does sameness mean? You see, the velocity over here and the velocity over here, they cannot be the same in the naive sense of the word. Essentially because they have different units. So you see, his question first was, okay, if this is a fluid, if all these phase space points is a kind of a fluid that they are flowing in phase space, and it's an incompressible fluid, and just imagine this path over here, this part of phase space as a tube, let's say, whatever enters should be leaving. They should be the same thing, same in quotes. That was the idea of the Lewis theorem also. But now it seems that it doesn't work so easily, meaning that we have to define what does same mean.
Are you suggesting that we introduce a scaling to make them the same? Multiplication factor to one of them to make it the same unit?
Well, there are a couple of things we can do. One thing is, okay, when we are combining them to form this phase space, let's not just put the P and Q there, let's just choose some momentum unit, some coordinate unit, and let's write everything in terms of that unit. That can be one possible choice. In that case, everything, the coordinates in phase space will be unitless, and now we can compare them. That is one choice. But let's see. I mean, in the derivation of the Liouville's theorem, there was no problem. And then we ended up having this problem. Why didn't we have any problem in the Liouville theorem, in the derivation? Let's go back to the derivation. Yes, it's no, here. It's over here, at the top of the screen. You see this line, okay, we didn't really make any sense out of it. We just wrote it down. We didn't really think, I mean, what does writing J as rho times V mean? We ignored it. We ignored this, let's say, technicalities. And then we came over here. You see, here there is no unit problem in this line. Everything seems to have correct units. Here, this has the unit of rho over t, this has the unit rho over t, this has the unit rho over t. What is the unit of rho, by the way?
Number of PQ.
What's the unit of PQ?
Should be 1 over volume.
H bar or joule second. That's the natural unit of rho. So here we have the rho over J, rho over T. This we have the rho times P over T divided by P. So everything has nice, neat units in the section. Well, the rho has the unit of 1 over H bar.
Why? It's a tuple. It's a tuple. How can...
No, you see, how did we define rho? The number of copies of phase space divided by the volume of phase space. In this phase space, the volume has the units of PQ. But PQ has the units of H bar. H bar and PQ have the same unit, or H, joule second. Okay, so here everything seems to be fine, meaning that the units are correct. At this point, we don't need to introduce actually any unit of momentum, unit of position. As we go on here, again, because of the same thing, the units are fine. There's no problem with the units. The difficulty in interpreting the result actually is over here. When we say J is equal to rho times V. A more formal treatment definition would probably start with defining a unit of P0, P0 for the momentum unit, define Q0 for the position unit, then Hamiltonian will be 1 over 2m P0 squared, let's say xp, plus 1 over 2m omega squared Q0 squared xq squared. Now the coordinates will be xp and xq. They will be unitless. You see this P0 and x0, they just disappear in the second step because we have the ratio of momenta in the second step and the ratio of coordinates in the second step. So in that second step, it doesn't make any difference what we introduce as P0 and x0. But if we want to interpret this V as a concrete example, I think it's kind of unavoidable to introduce that P0 and Q0. For example, this was a step where I just failed to ask, is this definition of J, does it make sense, and what kind of sense does it make? But then, of course, there is this question. If you change P0 and Q0, maybe rho will not be constant in your sense of the word along that line, along this line. You see, this rho 0, P0, they will be essentially correspond to stretching these axes. Now, if you stretch along Q, well, you will reduce the density at this point, but increase the density at this point. No, not keep the density at this point constant because you are just stretching along Q. So if you, okay, let's not go along. I mean, you can go over it. I mean, I would advise you, for example, just go ahead and, okay, calculate this integral. It's not a homework, but calculate that integral for the given rho and given v. It should give you, okay, it should give you 0 as the difference of those two terms.
I still don't get why didn't we just simply go 2 lines before and just calculated E from the first one?
E?
Yeah.
You see, E is, you can choose whatever E you want.
No, it would meaningless because it would give delta 0 unless I choose inside delta to be, sorry, any value would give us delta equals 0 unless I expect a certain value. I can use that value to evaluate both of them. That's it.
Positive?
No, if we went down,
Okay.
For example, from the first line, I could say that E equal Q squared m omega squared. I substitute this value and again under the square root, it would give me a number.
You see, eventually in this equation, I will set Q equal to 0, and here P is equal to 0. That's the point. Those are the points I'm interested in.
No, because if we set that, the
Yeah.
inside of the delta function would not be 0, so the delta function would be 0.
No, sorry. No, sorry, not 0. Q is equal to something, and P is equal to something such that the Dirac delta is 0.
Okay, or we can say that using this set, we could say E equals something in both cases, and it would give us the same number from the beginning.
Not really. You see, already if you go back over here, if you compare these two, this one and this one, and keep in mind, eventually we will set the argument of the Dirac delta to be 0. It will be Dirac delta 0 in both cases. If you just take the ratio, this is omega. Because you see the Dirac deltas, they will cancel, they are Dirac delta zeros. 2me, rho 0, they will cancel, so the only remaining part will be this omega. So whatever you do, you cannot change this ratio. So in that sense, the sameness in this description without using the new scales, etc., would basically correspond to having the ratio equal to omega. Between those 2 points, by the way. Between any other point, it will be different. The problem is we have units here. Now, in your next homework, I will just ask you to construct ensembles. Yeah, of course, you will not be doing, I don't know, infinitely many copies, but just take a system, make 4 or 5 copies of them. What happens in the microcanonical ensemble? What happens in the canonical ensemble? How do you define the temperature in this case? Hmm?
Are we construct like write simulation? Are we going to write simulation?
No, unfortunately. I do hope to give you more assignments that will require you to use computers, but not that one. Well, in one of your assignments, you also have the approximation of the factorial, no? Yeah. So you should learn to use computers. You just cannot run away from it. Even if you are planning to do pure mathematics. Yes, any other questions? About computers? This one? Yes, okay. Now, what will, you see, the problem here was, as you said, your claim was the velocity at these 2 points in phase space. Yeah. V1 and V2, they have to be the same. Okay, that was your claim. I agree with you. They should be the same. But the question is, what does it mean to be the same in a space in which the different coordinates have different units? I don't even actually know if it makes sense to talk about a space in which different coordinates have different units. So if the different coordinates have different units, those 2 points, those 2 velocities, definitely they point in different directions, so they will definitely have different units. So saying that they should be the same doesn't really make any sense if you don't specify what same means in these cases. There are a couple of choices. One of them is, okay, just to, from the beginning, make sure that the coordinates have the same unit or they are unitless. In that case, you can compare different numbers without units and ask whether they are the same or not. Okay, that is one thing. And now then, of course, there is a question is, what does it mean to have the rho constant? We say that rho should be constant. But that word, I would say, it means this equation. Nothing more. Then you will be complaining, well, can't I define a one-dimensional density? Won't that density be the same, constant? I suspect no. You see, basically here, you see, in Liouville's theorem, what we are using is this integral should be equal to 0. So rho times V2 over rho times V1. Let's say rho 2 times rho 1, this should be equal to 0. But we had already seen that depending on your units, V2 and V1, they will be different. So rho 2 and rho 1, they should also be different. Rho 2 and rho 1, not the rho at different points, but rather your one-dimensional density. You see, I mean, if you stick with the dimension full coordinates, rho 2 and rho 1, they should have the different dimension. They cannot be the same thing.
So can we say Liouville's theorem is not valid when you don't consider all the coordinates independently?
Well, let's see. This harmonic oscillator, simple harmonic oscillator, how can you construct a simple harmonic oscillator? One option, well, take a spring, a one-dimensional problem. Okay, that's a simple harmonic oscillator. A second option, take a pendulum. Well, a pendulum has 4 degrees of freedom. No, it has 2 degrees, is a 2-dimensional problem. So the phase space is actually 4-dimensional. But you have 2 constraints there. 3. You have additional constraints because the length of the pendulum is fixed. Well, you can treat that problem as a problem with a phase space of 4 dimensions. You shouldn't have any problem. Or have a space as a problem with a phase space of 2 degrees of freedom, the angle and the corresponding momenta. Liouville theorem should hold in both cases. They should be the same. But I mean, these 2 cases, they don't take into account all the coordinates as you state. Now, these 2 descriptions of the pendulum, either a 4-dimensional phase space problem or a 2-dimensional phase space problem. Okay, in both cases, I would expect the Liouville theorem to hold. And there should be a way to go from the 4 dimensions to the 2 dimensions, even in the general case.
What I mean, for instance, in 1D harmonic oscillator, let's equate the units of the coordinates, and let's use R on the ellipse instead of the P and Q. If you define R 1 dimension, then deriving the Liouville theorem, you will have the rho 1 dimension. Rho is just function of R. And since your velocities will be different with the...
Well, you see, one thing you should pay attention to is still, if you go from, you have a given system. If you want to describe your system, let's say dp, dq, you can define new coordinates, let's say dl, as you point out. Then there's the second coordinate. Let's say dh.
Yes, but by saying dp, dq, you are in 2D. You are in the hyper.
But you see, the problem is 2D. You already have your phase space is 2D. Then you solve the problem, you see that the solution is just 1-dimensional.
And by using a Dirac delta, you are transferring a hyper surface to a hyper shaft. But your Dirac delta has different behaviors at each point of that shaft.
Okay.
So it acts like another dimension exists, but you are calculating it on a hyper shaft. So it gives you the same result as the hyper surface. So it gives you the same result as the hyper shaft. So Dirac, defining a Dirac to go 1 dimension, I think is a problematic here, because you are using the divergence theorem in 2D, and then you are transferring it to 1D. If you use the divergence theorem in 1D, you won't get another result, not the same result.
You see, I always stick in 2D. Dirac delta function is just, it has a support which is 1D, but I don't go there anyway.
Also
you see, my rho is defined in 2D. It's not defined in 1D.
You are not using, you are not on the you are not in the space of hyper surface time. You are in the space of hyper shaft, but you are squeezing it.
No, I'm not. I'm not even squeezing it. You see, this rho, my problem, as I repeat, has a phase space which is 2-dimensional. There is nothing I can avoid. There is nothing I can do to avoid it. But then, in the microcanonical ensemble, this problem doesn't appear in the canonical ensemble, for example. In the microcanonical ensemble, I say that rho is equal to 0 if HPQ is not equal to E and not 0 otherwise. I'm still in 2D. But my function is non-zero only in a 1-dimensional hypersurface. That's what I'm saying. I'm not even reducing my dimension. Everything is 2-dimensional. Now, if you want to reduce your problem to 1 dimension, if you want to do that, I didn't do that. And defining rho as rho 0 Dirac delta of E minus HPQ does not reduce my problem to 1 dimension. It's still 2-dimensional. This is the way to go. Of course, this won't be L. I would advise you to go for T. Anyway, you can keep it this way. This is actually a so-called a canonical transformation. It doesn't change the phase space volume element. L, as you said, you can take as the length along the arc, or L can be actually the time. You can choose L such that L dot is 1. And H should be conserved. I'm not so sure, but H should be conserved somehow. So then this H integral, you can say that I can evaluate it. You end up with having L only. And then you can say that, okay, I have rho as a one-dimensional problem. Did I convince? I mean, give it a go. You see, there is a canonical transformation in analytical mechanics which takes you from PQ to, let's say, L, and let me just call H. L dot should be equal to 1. H dot should be equal to 0. I'm not so sure about this form. And dP dQ will still be dL dH. Rho as a function of this L and H will be something that like H minus E, and let me put rho tilde as a function of L. It can be a function of L. I'm not so sure now. This will be your one-dimensional density of states, one-dimensional phase space density. But you see, in Liouville's theorem, I'm not reducing my dimension at any stage. I'm sticking in two dimensions. The only thing I'm doing is that the system should be a Hamiltonian system. The equations of motions are given by the Hamiltonian. That is the only thing I'm using. I'm doing no dimensional reduction. So even in this problem, if I am to, what Liouville's theorem said, okay, rho should be constant as long as the constraint is satisfied. Well, this is what I have. Rho is a constant if the constraint is satisfied.
This constraint is 2-dimensional.
Yes, it's in 2 dimensions. I'm not doing dimensional reduction. Anyway, let's leave this problem aside for the time being. I see that most of you have already lost your interest. Would you like to give a 5-minute break? 5 minutes, not longer. Then I'm waiting for new questions. Five minutes started. If you don't want to go, we can continue.
Benim için mesela 2 boyutu tek boyuta indiren bir harita şöyle olmalı. Diyelim şöyle bir şeyim var. Şöyle bir şey. Şöyle bir şeyim var elimde. Volümü. Let's say we want to reduce the dimension to 1 dimension. So let's say this is my line, the ellipse of the ellipse is just like the ellipsis line. For me, reducing this problem to a one-dimensional problem, all the integrations that I need to take to that on that Dirac delta, which gives me 1, should be perpendicular to this line to make this one dimension. But in the ellipse case, the integrals are changing its directions and changing their magnitude. For instance, the dE, if you want to visualize it here, it is more than this dE. So you are defining a fictitious additional dimension to that line?
Okay, first of all, you see, what do you mean by dimensional reduction? That's the first question I will ask for. I mean, you see, hold on. Most of the time, for example, when people do call dimensional reduction, is they integrate out the extra dimension, the other dimension, so you are left with one dimension. Or you make some kind of a Fourier series in one of the dimensions, so the coefficients have one less dimension, etc. Now, here you are calling adding a Dirac delta as reducing the dimension. Because you see, in every problem, the trajectory in phase space is one-dimensional. Whatever the number of particles is, whatever the dimension of phase space is. Whatever the problem is, if you just pick up this object, the trajectory of this object in phase space is one-dimensional.
Yes.
Because it depends only on time t.
Yes. But I am not talking about the trajectory, but the possible states.
Okay.
If you, the reason we are not working on hyper shell, but we are working on hyper surface, was to get rid of this dE. I didn't want to add this delta E. I wondered what if we work theoretically without this delta E. This is a practical thing.
Okay. First of all, let's just continue. What's your purpose? Why do you need to introduce delta E to start with anyway?
Because in the book, by proving Lewis theorem, Patria introduced a hyper shell.
No, it did not. Lewis theorem doesn't do that.
He proved the Lewis theorem on the hyper volume.
No. Whatever the phase space is, he proved the Lewis theorem in that volume.
Yes, it is the volume.
Okay.
But if we fix the E, actually on the phase space, we need a line.
Yeah, hold on. First of all, forget about whichever particular system you have, forget about which ensemble you take. Then you prove Lewis theorem. Whatever your rho is, then the Lewis theorem, it should satisfy the Lewis theorem. Whatever your rho, whatever your ensemble, whatever your system is. If the system is in equilibrium, the phase space density should satisfy the Lewis theorem. Okay? Then it says, okay, what are the conditions what are additional conditions I might impose on my system? So that what additional conditions I impose on rho? Then he said, okay, maybe my system is isolated. If my system is isolated, the energy is constant. So he says that if that is the case, then rho should be 0 everywhere except then that surface. So that is rho. Now, of course, what is the value of rho at a particular point on that surface? I don't know, I don't remember now if he explicitly states it, he doesn't care. Every point should be equal. So that's why I have rho might have the form rho 0 times the Dirac delta. That is my, let's say, in general, rho satisfies Lewis theorem, whatever your system is. In canonical ensemble, there is no such constraint on the energy. So he said, okay, rho will be non-zero everywhere, and it will change as e to power minus beta e. So he is actually studying various different forms of rho consistent with Lewis theorem.
If I use a rho which is rho 0 times the Dirac delta, which gives me always, which gives me 1 in the integration over that perpendicular lines, should I get the symmetry?
Give it a go. First of all, does that satisfy Lewis theorem? Because Lewis theorem is the general restriction you have on rho.
Hocam, yalnız o şekilde mesela belli enerji source üzerinden volüm aldığımız zaman o sources hani volüm elementi içerisinde mevzuları olduğu için integral direkt sıfır gelmesi gereken mi? Orada bir sorun olmuyor.
Dirac delta has a non-zero measure. Dirac delta is actually the measure. Okay. Sonra dersten sonra yarın da oluyor. Okay. Other questions except on this one? You see, whenever you are doing some computation, at the end of the day, when we are doing physics, we are studying things that are measurable. So whenever you write an equation, okay, this is a lesson also for me, just can you measure it? Can you put some numbers there? So here, this was a place where I failed to ask myself, and now we are struggling all this time to understand it a bit deeper. Can you close the door? Yes.
Page 60, the expansion.
Page?
Yeah, this one, this expansion. The first term of the expansion comes
Okay, let's see. If you just open this page, if you say page 60, it will mean nothing to me. It will mean probably nothing to your students. So what are we doing here?
Okay.
What is this derivation about? So what are we trying to show? Can you summarize it?
This is after we start to study the energy fluctuations.
Okay.
And then we wanted to show that, or apparently he wanted to show that this energy fluctuation can be, energy distribution of these states can be given as a Gaussian, and then he wanted to show that this Gaussian is sharp at the average, and other values are negligible, other deviation to other values is negligible. So he wanted to expand the density of states, logarithm of density of states. He started by saying logarithm e to the minus beta e ge, but then he used the first term. The first term comes from is actually the logarithm of q. So I didn't understand this expansion.
Well, let's see. Now, any ideas? Any answers to your friend?
Because in page 51, he was doing something different, but he said specifically logarithm q equals, and he just put the first term as it is. So I didn't understand why he used this difference. And in the second line, I didn't understand why did he jump suddenly to k t squared cv, the specific heat in fixed volume. So if we just can elaborate more on this expansion, it would be great.
Well, let's go back. This is U, okay, the average energy. Any questions on how to calculate this average energy? Then he takes, okay, if I take the second derivative of the average energy of the system, he gets the variance of the energy. Which then he said, okay, it's du by del beta, which he said that I can write instead of derivative with respect to beta, it's a derivative with respect to the temperature, so it's kT squared del U by del T. And here you see, when he's taking the derivative over here, U is over here, when he's taking the derivative with respect to beta, he's taking the derivative only with respect to that beta over there. He ignores any possible changes in ER. So that basically means that when he's taking the derivative with respect to temperature, which is beta, he's keeping anything else that might modify the energy levels of the state. And those are the volume. If I change the volume, they will change the energy levels of the state. And the number of particles in the state. If the number is different, the energy levels will be different. So this time derivative is actually temperature derivative is a temperature derivative at constant volume and at constant number of particles. So he said that, okay, this variance of E is the derivative of the energy with respect to beta, which he said that he can write as in this form, kT squared times the derivative with respect to temperature, derivative of energy with respect to temperature at constant volume, but that is nothing but the specific heat. Now the heat capacity, sorry, not the specific heat, yes?
But are energy levels are a function of beta?
No. They are not.
Like the beta is 1 over T, right?
Yes, beta is 1 over T.
Okay, and the energy is a function of the...
It's the total energy is a function of the temperature. But the energy levels are the eigenvalues of the Schrodinger equation. which is independent of temperature.
And in that sum, we are summing over all possible
Microstates.
This
Yes.
does lead to the constraint that we have a specific energy mu.
Now you see, if you know the geometry of the problem, if you know the potential interactions between the particles and interaction with the environment, etc., then at least in principle you know the energy, possible energy eigenvalues of the system. Okay. Of course, then this system will not be isolated. You are not preparing it in a particular state. The system will be interacting with its environment. And at least in the canonical ensemble, we are imagining that it is in contact with a system at a temperature T. So then, of course, we can talk about, well, in this case, we won't be able to talk about the wave function of the system, but we can talk about the various probabilities that my system will be in different microstates. Those probabilities are temperature dependent. But the energy eigenvalues of those microstates are temperature independent. Of course, they depend on the potential, which if the volume depends on, well, the potential depends on the volume. So in that sense, this temperature derivative is at constant volume, constant number of particles. And at constant volume, heat capacity is just the derivative of the internal energy as a function of temperature. Okay, so this is one thing we have. Then he says, okay, so this is about the averages and the fluctuations. Then what about the probability density? You see, we have this Boltzmann weight. Now, what does the Boltzmann weight do? It's essentially the probability of a given microstate. So if you have a microstate, I can ask you, what is the probability that my system will be in that particular microstate? And that probability is a function of the energy. As energy increases, that probability decreases. So in fact, on a one-by-one basis, the most probable microstate is the one that has the least energy. But if you ask me the question, what is the probability that the system will have such and such an energy? That's a different question. Because that probability will be the product of two things. How many microstates are there that have that energy multiplied by, well, since all those microstates have the same probability, what is the probability of that of one of them? So it's the product of the number multiplied by the probability. That is mainly because I'm not asking you what's the probability that my system will be in one particular microstate. What I'm asking is, what is the probability that when I measure the energy of the system, it will have such an energy? If there are more states that have a given energy, then the corresponding energy probability will be larger. So that is why we have the probability of a given energy is a product of the Boltzmann weight, which is proportional to the probability of one microstate, multiplied by the number of microstates that have that energy E. Then the question, okay, so we have this expression over there. Now here it goes over here. Now the expectation is that, like in your first homework problem, that probability distribution will be very much peaked. So if you make an expansion in that probability distribution, the convergence will be, well, quite poor. Rather than expanding that probability density of a given energy, what he does is he expands the logarithm of that. If you take the logarithm, it just flattens out your function. It will be a broader function. So its convergence as a function, as a Taylor expansion, will be much better. So then he looks at this one. What about this logarithm of e to power minus beta times g of e? Okay, of course, then let's see. Then he claims, okay, this is the first term. This is the second term. Now, let's say, well, let's see. At E is equal to U. Well, he has logarithm of e to power minus beta E GE expander on E is equal to U. Well, the first term is just instead of E, put U. This is the first term. The second term, well, take the derivative with respect to E. And then set E is equal to U. Then, of times E minus U plus the second derivative. Here we have the logarithm. Multiplied with E minus U squared over 2. Then plus all the other terms. Okay. Well, let's see. Just use the properties of the logarithm. The first term is minus beta U plus logarithm of G of U well, this term is 0 because U is just the most probable energy value. Well, the definition of the most probable, technically the most probable energy value is you just take the derivative with respect to E and equate it to 0. And then you have the second term. Well, what is this? What was G of U? Density of states. So essentially, if you just multiply it by the thickness of a shell, it gives you the number of states. So G of U, up to this multiplicative factor, the thickness of the shell, is the number of states which lie within that shell. But the logarithm of the number is just the entropy.
How did we say that? I mean, GU is number of states that has this specific entropy, not the whole, not all of them. But
Sure.
entropy usually sum all of them.
No. You see, remember how we defined the entropy? This
Did
was
we say that entropy is logarithm of the okay, omega, or instead of omega it should be Q, the partition function?
well. Let's see. This is the, and then if we stick with the microeconomical ensemble, let's say, where omega E was, what was the definition of omega E? Not the mathematical expression, the meaning of omega E. Number of states of energy E. Then we said, okay, we don't really like that number that much. Let's go for sigma of E. It's hard to calculate omega E directly. Let's calculate sigma of E, which was number of states having energy less than E. Then, well, then omega E, if we, let's say, integrate this omega E, between, let's say, E minus delta over 2 to E plus delta over 2. Or let's say it wasn't the density, so let's not integrate it, but sum over it. This should be equal to sigma E plus delta over 2 minus sigma E minus delta over 2. This is derivative of sigma with respect to E multiplied by delta. Well, then we said, but this essentially means that omega E is approximately this one. But you see, this is what we call G of E. It's the density of states. And now we said, okay, but you see, logarithm of omega of E, which is the entropy, this is logarithm of derivative of sigma with respect to E, plus the logarithm of delta. If you like, you can just multiply this by E, divide this by E, to make sure that the units are fine. Then we said, okay, this number over here is something of the order of 10 to the power 23, whereas this number over here is something like 23. Then we said, okay, we can just ignore it. And similarly, this E doesn't really contribute much. This will be more or less logarithm of G of E, numerically speaking. Of course, again, I repeat, here we are just ignoring some conversion factors, etc. But whatever you choose, it doesn't really make any difference. So here, that is also what is done. This logarithm of the density of states at a given energy is just the entropy divided by K. And that is the first term, minus beta U plus Sk, this one over here. And then we have this term over here.
Sorry, I don't understand why the second term vanished in the expansion.
Okay, so let's look at this one. E to the power minus beta E times G of E. We said that this is P of E. This is the probability density for energy. Well, if you would plot this, E to the power minus beta E, it has a maximum value when E is equal to 0, it is this one. GE, it is the state which has the minimum energy. There's just one state which has the minimum energy. As E increases the number of states, the density of states increases. This is E to the power minus beta E. This is G of E. Now, if you multiply them, this is more or less what you get. And here, let's say U star. Now, U star is the most probable energy. Then we have the U, which is the average energy. But their difference just goes to 0. So instead of U is basically the most probable energy, but so derivative with respect to E of E to the power minus beta E, G of E, evaluate that E is equal to U, which is for all practical purposes U, or U star, which is equal to U. This is 0. This is the definition of U. So that's why we have this first derivative term is 0. The second derivative term, if you just take these derivatives, it just turns out to be the average energy or something like that. So I mean, you have to convert this second derivative into this expression over here. But basically that is, I mean, you have to convert it to the derivative of u with respect to beta or something like that. So what this proves essentially is that this probability density, the logarithm of it is, there is no linear term, you start with the quadratic term, there's an overall constant, but that is Gaussian. Now, in which sense? Well, if you look at over here, how does this scale as the number, as your system? It's E minus U. E minus U is the average fluctuation from equilibrium. It scales as E minus U squared scales as N. CV over here scales as N. So that number doesn't change with N. You can go and calculate higher order terms over here. The next term will go as 1 over N. Well, in fact, this is the proof of the center limit theorem in mathematics. It just goes to 0 in the thermodynamic limit. It's negligible. And here, if you look at this expression as a function of, here that what it actually says is that if you look at this basically means that if you just factor out u, because you are looking at relative fluctuations from u, but if you factor out u, the dispersion is inversely proportional to the average energy, which means in thermodynamic limit it goes to 0. The fluctuation of the energy will always be kT squared times the square root of kT squared times CV. The fluctuation will scale as n to the power 1/2, whereas the energy will scale as n, and they are kicking us out. Okay. Any last questions, or we can continue outside? So see you on Wednesday. The exam is 2 weeks from now. On Wednesday, we start during the class hour and you have until 5.